Okay, we are at the last section on eddy currents. And before we go to the PowerPoint, I'm just going to take a little piece of aluminum. This is just off of a can of a Waterloo. I tend to like the Waterloo flavored drinks. So I just cut a strip. So this is a piece of aluminum, and I've got some neodymium magnets just taped to this little um, clothespin. Uh, and some of you younger folks may not know what a clothespin is, but we have some around the house. And I'm first, if I drop the aluminum, you'll see it just drops it. The gravitational acceleration. Now let me drop it through the magnets. Let's watch that again. It certainly slows down. You can see that it's a little bit slower. Now you can look up. You can find a lot of videos where people drop a neodymium magnet in an aluminum tube, and you see the same effect. The neodymium magnet, they'll drop a quarter through the tube, and it drops the way you would expect it. And they drop a neodymium magnet through the tube, and it slows down. And you can see here that there's a difference here. You drop this like this, and you drop the aluminum through the magnets, and it goes a lot slower. So there's a what we're oops, I think I'm at the wrong spot. Let me go back. There we go. This is the, yeah, there we stopped with motors. Here's the eddy currents, and you'll see. Well, let's get to the lectures. As the plate enters or leaves the field, the changing magnetic flux induces an EMF, which causes the eddy currents in the plates. So as we drop this, Lenz's law says that a current will be induced such to oppose the magnetic the change in magnetic field. So as we drop this through here, it's a growing magnetic field, so it induces a current to oppose the changing magnetic field, and that it actually that opposition actually forms a break. Again, you can see how it goes slowly through the magnet. So as the plate enters or leaves the field, the change in magnetic flux induces an EMF, which causes eddy currents in the plate. So the eddy currents, the magnet forms the eddy currents in the plate. So as it first enters the magnetic field, it's a growing magnetic field, so it'll induce current such that it wants to oppose that uh, uh, current, and it it opposes it, so it breaks it. And as it's exiting the magnetic field, it wants to reinforce it, so it reverses the current in the plate. Let's go on here. As the conducting plate enters the field, the eddy currents are clockwise. As the plate leaves the field, the currents are clockwise. Now, if you want to reduce the braking effect, you can cut slots in it. When slots are cut in the conducting plate, the eddy currents are reduced and the plate swings more freely through the magnetic field. Now, what good does this do? What do we use it? Well, if you ever used a triple beam balance in lab, I know most of the time we use the little electronic, but if you use a triple beam balance, you will, on one end of it, there's a little aluminum plate, and there's these magnets inside, and it damps the oscillation of the triple beam balance. So it's used there. If you've ever ridden the Poltergeist at Fiesta, Texas, when you exit the Poltergeist and go where the return, where the cars return to the beginning, if you look at them, you'll see these veins sticking out of the uh, these aluminum veins sticking out of the cars, and you'll see that they run into electromagnetic brakes. So this is just a braking system used. So I mean, you can look up eddy current brakes, and you'll find um, a lot of interesting applications. Anyway, so that ends our eddy current. That ends chapter 30.